Okay, so as Murat has introduced, I'm working in information extraction from electronic health records. So before starting my research or before narrow downing the things into the domain of health records, I was working on how to deal with the natural language text. Like whenever we're talking about the machine learning models, we say that the models will take the data in the form of numbers, and then numbers are understandable, and the statistical operations can be performed on the numbers. And then very well it can understand the numbers, and whatever operations you are performing on those numbers, the insights from that data will be extracted, and we are calling it an information. But then when we are talking about the text, especially when we are talking about the natural language representation of a particular data, we can say, then just representing that particular text in the form of number and then applying our models may not give you the insights as per the natural language understanding of that particular text. So basically word embedding starts from there. So today I'd be discussing very basic application of word embedding. I'll be comparing 3 word embeddings here, and I'll also tell you about what can be the research domains which are available into embeddings, and which all other embeddings are also there, which I am not discussing today. I won't be able to discuss today rather. So I'm discussing a very basic application, that how can we use word embeddings in identifying the duplicate statements. So if I have, let's say, for example, one statement, one sentence in my hand, and there is another sentence, and if I want to find out the similarity between these two sentences, then how can I make use of the word embeddings? There is variety of application wherein we can use this. Like for example, especially when it comes to healthcare domain, we are trying to find out how similar two patients are. So in that case, we will try to vectorize maybe their electronic health records, and then we'll try to compare these two vector representation to find out whether they are similar or not. Or there can be other application domains, such as if there are, let's say, for example, movie reviews, and we are trying to find out whether the reviews are similar by two users or not. We can even use it further. We can even extend it further for collaborative recommendation and all. So even if the application is quite basic here, but it can, once it is understood, once you use this, and once you know how to use these models, then you can very well extend this basic application into some major downstreaming task into NLP. So my today's agenda of discussion would be, I'll introduce you to the semantics in NLP, why we need semantics, why we need to deal with the semantics basically. What is the role of word embeddings in understanding the context? So whenever I'm talking in natural language text, it is very much important to understand the context. Like for example, if I'm saying, I'm going to bank to deposit a money, and I'm taking a walk on a river bank. So here the bank keyword may be similar in both the sentences, but the context in which the words is uttered is totally different. And if we are representing this bank keyword in a similar representation, then that may be a wrong insight from language understanding perspective. So I'll try to explain you why we need to understand the context when we are representing the words using the vectors. How can we represent the context using the word embedding? And then we will compare BERT, GLOF, and ELMO. These 3 very popular word embeddings these are. And there are many more which I'll list down at the end of the presentation as well. I'll show you the Python implementation, and I'll also show you I'll also give you the references from where I have downloaded the models and how I have used it. And then I'll discuss a few open domain research problems in the world of embeddings. So to go ahead, let's first try to understand that when in the data science, whenever we are building the model, we are saying that we have a data in our hand, we load the data, we may collect the data, we may scrape the data, we may collect the data from various sources, and we clean that data. Rather, we make it ready for, let's say, modeling purpose. Once our data is ready, then we try to transform the data into the model. And most nowadays, quite a popular approach is that we work a lot on the feature engineering. We try to extract maximum features possible. We try to represent that feature space in the lower dimension, and then we train the model. And at last, we evaluate the models and we test our models whether our models are working good or not. This scenario is pretty what we can say fit into the scenario wherein your data is in the form of numbers, or for that matter, even if you have a categorical data wherein you can represent the data directly in the form of numbers. Like for example, if I'm saying I'm having a column gender in which there is male, female, then I can just represent it by a number 0, 1. So wherever in my data male appears, and if I say it is 0, or wherever in my data female appears, and if I represent it with the number 1, it may not make much difference in understanding of the data, as it is a categorical data for which I'm representing it in the form of numbers. But when I'm dealing with the text data, let's say, wherein I'm trying to understand the meaning of the sentence. Like for example, I'm saying that this movie was good, the actors were also good. Or if I'm saying that what a good movie, it was such a waste of time to watch that movie, right? So here, when I'm trying to understand the meaning of these two sentences, we being a human being, we do understand the sentiment or the opinions here. But then when we want to build a model to understand this, and if I use very much syntactic approach of saying that if there are positive words in my sentence, then I'll say that the sentence may be positive, or if there are negative words in my sentence, then the sentiment behind that sentence may be negative. In such situation, the example which I gave you just now, you'll come to know that the second sentence, what a good movie, it was waste of time watching it. So here as well, as there is a good keyword in it, and good keyword is, let's say it is already annotated, we'll not get into that because it is altogether a separate learning module. But then if I say that it's a good is a keyword there, so my model may assume the second sentence to be also positive, right? So understanding the text is little different than that of understanding or extracting or building the model by using the data which is in the form of numbers. These are three popular models which I have listed down here, which are very much popular when we are talking about the categorical data. Initially, when in natural language processing, these are the initial models when the context was not that popular, or it wasn't, when context was not introduced. So these models are talking about how to represent the text data in the form of the vectors, because our model can understand only the numbers, right? So we need to convert our text data into the number. So I'll start with the basic these three models one by one. Let's say the first model is a vectorizer or encoding. So in the encoding or vectorizer, let's say for an example, I'm trying to represent this model, this particular data. The column is animal and the values are dog, cat, sheep, horse, and lion. If I'm trying to represent this particular text representation in the form of numbers, and the vectorizer or the encoding method will just encode the data in the form of numbers like this. So you can see it here on the screen that for every value in this particular column, it is creating a vector, and if that particular that at that particular index, like dog index is 0, there will be 1, rest all indices will have 0 value, and respectively we can see the vector representation of the cat, sheep, lion, and horse. So we can very well say that here the goal of converting our text data, dog, cat, sheep, into a number is achieved here, right? But then when it comes to representing it at more semantic level, will it be sufficient? That we will see once we study all these three models. So the next model is TF-IDF, term vein, and this model says that here when I was representing the terms from the data in the form of the numbers, I was actually not considering importance of those keywords, right? So whenever we're talking about the natural language, whenever we're talking about the text, we say that every word in my document is a feature, right? Every word in my document is a feature. Let's say there is an essay written on school, and then I want to, let's say, design an auto evaluator for this. uh, I need to understand what my model should extract here. My model should extract the keywords which are in the context of the school, and then how I'll come to know that whether the keywords which are important here. So I'll try to find out which are the keywords which are frequently used while writing the essay, or if there are more than one documents. If there are more than one documents, then I may say that I'll see that which are the keywords which are frequently repeating in each document. Because why are we saying that we also need the keywords to be considered from the various documents? Because if we simply consider the frequency of the words, then there are words like the, and, of. These are the words, we call it stop words in natural language processing. These words will have a high frequency, but they are not of importance, right? They have very less, they're adding very less value uh, when it comes to understanding that document. So how will you understand the document? You will understand the document by the keywords which are important. How will you find the importance of the keywords? I said, okay, I'll try to find out that how many keywords are occurring frequently. But then frequently occurring keywords like these stop words may not, with only the frequency, I may not be able to capture the importance of the keywords. So what do I need? I need something more than that, and that is called as inverse document frequency. So here in the inverse document frequency, you can see that if I have, let's say, two documents, A and B, and these are the list of words. This is also called as vocabulary in natural language processing. So these are the unique appearances of these words in these two documents, and I'll try to find out the inverse TF IDF matrix. So what is this TF IDF matrix? Term frequency and the inverse document frequency. So term frequency means how many times that particular keyword has occurred in this document, let's say A. So if there are total number of seven number of words in that document, for example, and how many times this the has occurred. Then similarly, in the second document as well, this would be the term frequency per document, and the inverse document frequency would be that in how many such documents in our corpus this particular word has occurred, which, and the log of it. And then we will say that uh, now we will multiply the term frequency into the with the inverse document frequency, and we will calculate the importance. Then you can see here that the TF IDF value is 0. That means even if it is repeating, it may not be of that importance. Let's look at the keyword car here. For the car as well, car appeared only in document A. It is not there in document B. So the term TF IDF for this is 0.043. Similarly, we will keep on calculating the TF IDF for each and every word in our data. So what is these values? What are these values? These values are trying to tell you that is how important this keyword is. Why do I need to find out the importance of the keyword? Because I'm saying that whenever we are dealing with the text data, what are our features? Our features are word in our text data. Now there can be many words when I'm trying to represent my input using the natural language text. So from those many words, I need to just consider only the important keywords. So this is in when we were talking about the first encoding method, therein it was considering each and every word from the data to be a possible feature, or rather each and every word to be a feature. But now the TF-IDF frequency matrix is telling us that there can be few words which you can select, and that can be the important words with which you can represent the data set or the whole corpus, right? Now, there was another evolution into finding out the features from our text data, and that was bag of words. So in the bag of words, what are we saying? We are representing the bag. It is a literal meaning that we have the bag of words. So let's say, for example, we have these 4 documents. We have the red dog, cat eats dog eats food, red cat eats. And now we are representing each and every document with the number of with the bag of words in it. So I have the red dog being 1. Okay, and from the whole corpus, so this matrix is going to have the representation. So here in the column heading, you'll see that there will be vocabulary, that means each unique word appearance from the whole corpus, and then you will try to find out, you will construct the bag of word, right? And now from here again, what is the advantage of this bag of word over the earlier 2 models? It is again trying to give you the precise features as compared to the long what we can say, the longer features or more features, in other words, right? But then here when I'm saying, let's say I'm using all these models to perform some downstream task. Let's say, for example, understanding the named entity, finding the named entity from my keywords. Yeah, it also encodes, yes, Sumit. There are 2 ways with which we represent the bag of word. We can represent it with whether that particular word is present there or not, and you can also represent it that how many times it has occurred. So it also, there are various ways with which you can represent it. You can also represent it with the count. But then what are the drawbacks? What are the drawbacks of this system? All these 3 representation, that you cannot capture phrases and multiple word expressions. Like, for example, if I have, whenever I'm representing my data in the form of natural language text, then what is important for me, I need to capture the order, the sequence of the words. Like, for example, I'm delivering a lecture today, and today I delivered a lecture. So there is a difference when it comes to understanding this text. And so I also need to understand the sequence of the words here. Whereas these 3 models, language models, fail to represent the sequence of the words. So we need to have a model which may work better with the order dependencies. Now, there is something in the chat. Okay, yeah. So now there is another, whenever we are talking about, oh, I'm sorry. Yeah. So whenever we are talking about the natural language representation, order is important. That is what we have seen. But we have seen that whenever we write something, there can be probable misspellings as well. There can be out of vocabulary words as well, the words on which your model may not be being trained. So these models fail to work on the misspelled words. These models fail to work on the words on which they are not learned. So and it does not even understand the context. Like, for example, the example which I gave you, that I went to bank to deposit a money, and I'm taking a walk on a river bank. So these models are going to represent the bank keyword with the similar numeric value by using any of the model here. But then when I'm saying, and when I'm trying to understand the meaning of this bank keyword, the bank keyword has got a different meaning in the first sentence, and it has got a different meaning in the second sentence. So it also fails to capture the actual meaning of the word, right? So what does that mean? That means it is not understanding the context, right? So we need to know the context. We need to capture the context to understand the meaningfulness, or to understand the importance of the keywords. So let's see why this context is that important. So this is the diagram which I've taken, and this is the image which I've taken from the LinkedIn, but a good image here. They're saying that if you do not consider context while representing your text data, then what you may consider will be a noise, and then garbage in, garbage out. We know it is into it is the saying into data science. So here you can very well see that what is the context here. Context is these rods which are putting that shadow on the dog's body, right? And because of this, the model may identify this, even if I'm taking an example of the image processing, but uh, just to tell you that what is context exactly, I've taken this example. So here, as context, these rods are not known, then your model may misunderstood this image to be a tiger image, whereas it is a dog. You can see it here. So in the similar way, if we are not understanding the context well, then we may not be able to understand our data, or we may not be, in even worse, that we may not be able to extract the information which we need from the text which is being taken as an input to build our model or to train our model, right? There's something in the chat, I'll check quickly. Oh, so as now we have understood that context is important, then which all are the language models which are capturing the context? So the very much popular language model is Ngram model. In the Ngram model, how do we represent the context in the text? So the very first approach with which they started thinking about the context is that try to consider the neighboring words of the word which you are trying to understand. Okay, so and the neighboring words can be captured by defining the window. So let's say I'm trying to understand the context of the bank in the first and the second sentence. Then I'll say my window is 2, and then I'll say the neighboring 2 words to understand keyword bank. So the neighboring 2 words in the first sentence and the neighboring 2 words in the second sentence are different, and definitely now my model will understand that the bank in the first sentence and the bank in the second sentence is having different context, right? And this is the basic of Ngram models. So in the Ngram model, I'll give you an example how it constructs the Ngram. So there are unigram, bigram, trigram, 3, 4, 5, like Ngram. N can get replaced with 1, 2, 3, 4, and that model you can build. So in the unigram, you are saying your N value is 1. That means each and every word is being represented as a feature. So I am happy to be here. So I am happy to be here. Each and every token will be considered for processing. If I'm considering bigram, so my window size is 2 here, right? So my window size is 2. And then how will I consider the context here? So to understand I'll consider I am. To understand M, I'll consider M happy, happy to be, and be here. So this is how we represent the data in the bigram. And similarly in the trigram, I am happy to be, sorry, and to be here. So now, when we are representing, what can be the advantage of representing this? So we can very well see that we are able to see, we are able to capture the neighbors of the words, right? So if we have the neighbors, then the understanding of the word will be little more, understanding of the context will be little more, right? So, but then it also has got some drawbacks. The drawbacks of the Ngram models are that it does not capture the longer distance context. Like till what I can go till 5 grams, 6 gram. But then when I'm trying to perform the analysis on the whole discourse of the document, then I may be interested in finding the relationship between the first sentence in the document and the last sentence in the document. And my Ngram model will be quite complex if I keep on increasing the value of the N, and then if I'm keeping the value of the N as less, then it may not be able to capture the longer distance context, right? It does also have the limitation of out of vocabulary words. Like for example, if I'm training my model only on, let's say only on this one sentence, and now if I add, I am happy to be here with you, my model may not be able to understand with you as it is not being trained on it. But it is still very much popular in the downstream task of prediction, sequence prediction. It's a sequence level sequence model. Like for example, we nowadays we've seen that whenever we type something in the inbox, like when we compose the mail or even on our WhatsApp or mobile chats, when we type something, it predicts us the next word, and that prediction can be such kind of applications can be implemented using n-gram models. But then we are again trying to go little beyond this. We are saying that we are not only dealing with the word level analysis. We are trying to deal with something more than that. We want the sentence level analysis. So yes, yes, because here when I'm assuming, yeah, yeah, in the chat there's a question that it all depends on how many words I want to grab. Yes, I'm assuming here the n-gram model's assumption is this, that the context is dependent on the neighbors. So as it is assuming that context is dependent on the neighbors, so my window I'll decide the window that how many neighbors I want to have a look at, right? So yes, I totally agree with you that it totally depends on how many words I want to grab. But then it is a proven fact that if your value of n keeps on increasing, the model becomes complex. And if you reduce the value of n, then you may not be able to capture the relationship between the words which are at the longer distances, right? Yeah, so that is what I'm coming to, that if how to deal with the unseen words, Sumit. Yes, I'll come to that question. So yeah, we do have, if the count of 0 is there, then we do have the techniques, like for example, we use smoothing. In the smoothing, we try to, if the probabilistic models are there, we say that I have seen that particular word at least once. We will pretend that I've seen it at least once, and then we try to deal with it using the 0 probability. So we say +1 in the numerator and plus v, the size of the vocab in the denominator, and this is how we deal with the 0 probability problem, Sumit, when we implement these models, right? Yeah, so when we are, yes, John, when we are building our language models, we rather for any NLP model, whenever we are building, our first pre-processing pipeline starts with this, that we have the sentences in our hand, and we tokenize those sentences first, and after tokenization, we remove the stop words. Okay, we remove, because we consider stop words are not going to add any value to my processing, right? So we remove the stop words, and then we say that whatever list of tokens I have, those may be the important words. Okay, so we do remove these stop words. I'm just trying to introduce you to the models which are the early models of the embeddings. So, and why there was a need of the word embedding. So I tried to show you the flow, that we just had the numerical representation of the words, but that was not sufficient. We said that we need a context. Then we assume that neighbors are the context, and then the scientists or the researchers came up with the n-gram model, which is assuming that if I capture the neighbors, I may be able to capture the context. Yeah, but then still it does have limitations in representing the out of vocabulary words. It does not capture the semantic relationship between the tokens, because it is just saying that if the words are occurring together in a particular context of in a particular window, for example. So what can be the solution to this? So of course the word embeddings is to the rescue here. So now we are actually entering into our today's discussion. So what are word embeddings? Here, the first drawback it tried to overcome of the n-gram model was that understanding the semantics. So it comes from the distribution semantics. So what is a distribution semantics? When I'm representing a word, okay, when I'm trying to understand a word, we human being, we try to understand a word with respect to the characteristics of it. But when I'm saying that understand the word only with respect to the neighboring words, then sometimes those neighboring words may not be giving me sufficient explanation about those words, right? So these distribution semantics are not understandable, and the word embedding is facilitating the distribution semantics. It is a simple one of n or one hot encoding again, but then with respect to the dimension, okay, it has got a dimension. every word or every feature will be represented with respect to dimension, and this dimension feature is nothing but capturing the context of that particular word. I'll show you how. So in other words, we can say a token or a word or a phrase, sentence for that matter. Nowadays, we have doc to wake, we have word to wake models wherein it takes whole document and then can represent it in the form of vectors. So yeah, is mapped to a real value vector representation that allows words with similar meaning to have a similar representation with lower dimension. So what is the aim here? The aim is that I have a word, right? I want to represent that word. I want to represent that particular word with the real numbers because my models understand the numbers. But when I'm representing that word with the form of numbers, I do not want to lose its meaning. So whatever number transformation I'm doing, that number transformation should be with respect to the meaning of that particular word, right? And so here, if that particular word is being used in a particular context, it should have a different numerical representation. Whereas if the similar word, if the same word is being used in different contexts, will have a different numerical representation. So if bank is being represented, let's say with some real value, let's say 0.32, in the first sentence, the example which I gave you, in the second sentence, it shouldn't be 0.32. Otherwise, it will again say that the bank means the same in both the sentences. So this is what we are trying to achieve by using the word embeddings. So here, this is the reference from where I've taken this example. So here we are trying to understand how the word embeddings are, how the words are represented basically. So I'm saying that I'm representing a word with respect to the higher dimension, but then we still have a restriction that we cannot simply keep on increasing the size of our data. Then our model will become bulky. It will take much time to understand the things, right? So we want to understand all the characteristic of that particular word, okay, so that we'll be able to capture the context. Still, we have the lower dimensional representation of that particular word. So this diagram very well depicts this. Like for example, if I want to represent cat keyword, then with respect to the dimensions, living being, feline, human, gender, royalty, verb, plural, right? So these are the dimensions, or to be more understandable, to understand it easily, we can say these are the characteristics with respect to which I can represent the context of the cat, right? I can represent the context of this particular word. And this is how cat would be represented with respect to these dimensions, right? And now this is being represented with seven dimensions, right? It is describing one keyword with respect to 7 dimension. And now this 7D, this 7 dimension is converted into 2 dimension. This is how you can say X and Y. This is represented into 2 dimension. Okay, this representation is what we need to understand today, which is a word embedding. Now, what is the advantage of doing this? So cat is being represented with respect to these 7 dimensions. Kitten is also being represented with respect to these 7 dimensions. So it is carrying some information, right? It is carrying some information with respect to the characteristics. Cat, kitten, dog, houses. Now I'm representing these words even in the 2-dimensional. And now let's say I'm just taking the difference. Let's say I'm taking a simplest, let's say Euclidean distance I'm taking here. The Euclidean distance will also tell me that cat and kitten are more similar as compared to cat and houses. Cat and dog is more similar as compared to cat and houses. So here you can very well see now that it has understood the context, right? It has understood that kitten and cat are more similar because cat was also represented with respect to these characteristics. So when we were representing this particular word in the multidimensional space, feature space, and then we reduce this dimension so that we can represent it in a lower dimensional space. That is our requirement for building the model. But then we did not lose the context. Rather, we carried the context of that particular word along with it. And so these models are very well, intelligent to carry the context of a particular word along with it. right? So this is about the word embedding. There are very simple steps. Like for example, suppose if I have list of words, I just need to provide the vocabulary and the vector dimension. So the vocabulary would be, let's say I'm talking, if I'm trying to I'm trying to build a model in, let's say, healthcare domain, then I'll try to build the vocabulary only in the healthcare domain. Then the warm keyword will have a different meaning when I'm representing warm in the healthcare domain, right? It should be it should carry the context. It should carry the context such that the warm in the healthcare may be talking about fever, or maybe talking about whether the person is well or not well, right? So now this is how we represent it. About converting the data from 7D to 2D, these are deep learning models. As these are the deep learning models, they have their ways of converting it. Today, as we are discussing only about the representation of the data and comparison of these word embedding models, so we will really not get into the dimensionality reduction, but there are many ways with which we reduce the dimensionality. Like we have PCA, we have many more statistical approaches with which we reduce the dimensionality of a vector. I hope that answers. Right. So now we will try to understand it. Yes, John. As you're saying that the example which I have given is in 2D, but to understand. So if I say that I'm representing cat with some numerical representation, and if I'm representing kitten with some numerical representation, even if this is 2D, but then my this will work if it would have been just a categorical feature. But I'm saying that this is not a categorical feature. I'm saying this is a natural language text, right? So it has got something deeper meaning than that of this, right? But then this deeper to capture this deeper meaning, I'm trying to represent that particular vector with respect to more dimensions, so that I can carry much more information about that word. Okay, so we are first trying to represent a single word with respect to many more. We are trying to expand the dimension here because we want more information to be captured along with that word. Yes, and yes, Sumit, you're right. We are losing the information when we are trying to convert it from this to that. But then it is also carrying the information which is more than that of just representing it with a numerical value for cat. Okay, so it is carrying more information as compared to just representing it with the cat keyword. Yeah. So now we will come back. We will actually. Okay. Yeah. I hope that solves the answers. Yeah. So these are the models which I'm trying to compare today. So there are these context-based models which are available. So this is the process. What do we do? I wanted to explain this process with an example. So what do we do here? We have, let's say, list of words. From the list of words, we will provide the vocabulary. The vocabulary will be our domain specific words, and we will also provide the dimension that I want to represent this particular word with this much dimension. Let's say maybe you will say that I just want the vector of size 10. Someone may say that I want to capture as much information as possible. Then I want to represent the vector with 200 dimension. So it is totally up to you. It is totally up to the model, or it is totally up to the resources which we have and how much we can afford. Now for each word, what it does, the one hot encoding will assign the index. Okay, it will assign the index, and from that index value, now it will again represent from the vocab. It will capture the index of it, and then this, you can say, a kind of index here, and from that index now it will try to find out the dimension with respect to how many features you wish to represent for that particular word. And so this I can say that I want to represent the particular word with respect to the 7 features, right? And this is how we try to represent a particular word in in the higher dimension so that we can capture the more information about it. Right. Okay, so now coming back to the models. So these are the models which I'll be discussing today. These are the models which are already available. These are pre-trained models. What I'm doing as I'm in the college, and in my college we always face a problem to find out the project titles which are submitted by the students, whether they are repeated, like whether the similar project was being done in the last year and last year or not. So here we used to earlier we used to manually find out. We have a list of projects for last 2 years, and whenever student is submitting a project title, we are checking whether this project title is similar, is same with the as compared to the previous 2 years list which we have. Right, we used to do it manually, but as and when our batch size keeps on growing, and as and when our intake increase, doing this manually was difficult. And then we learned about this automation as well. Then we thought of using let's say string similarity, and then we did build a model, rather an application software we can say, using which we were trying to find out whether the project title which is submitted by the student is repeating, or it is same as that of the last 2 years, or is it matching with any of the project titles which were submitted in the last 2 years. But then it was string matching, and then if at all student tweak with the keywords, the synonyms, it may not work. Or rather sometimes it even if they are not doing this intentionally, unintentionally as well, if the similar title is being selected and if the strings or the words are different, then it was not identifying that the particular title is similar as compared to the previous 2 titles or not. And then we learned about this context-based word embedding model, and we thought of using these models to semantically find out the similarity between the titles. So a very small experiment we have done. It is very basic experiment wherein we are simply using the pre-trained model. We did not customize any of the model. We have kept the default settings as it is. Only the application what we have built is that we are providing the list of project titles and then converting it into a vector. And now a query which is submitted, which is nothing but the title which need to be approved for this semester, let's say. And now we are comparing this, it is also getting converted into the vector, and we are comparing this vector representation of the title with each and every vector representation of the project titles which were done in the last 2 years. And then we are finding the cosine similarity between the 2 vectors. And if the cosine similarity is high, then we are rejecting that title. So it is very simple application which we have built, and literally it took hardly 2-3 days, but then it reduced much of manual work for us, and a good automation we could achieve. So we tried to see, we tried to implement it with various models, and which model will give us better output. So especially for this today's talk, I thought of implementing it using 3 different models and just comparing which one is good. And I'll show you how each model works and how our project, or rather how our application is behaving for each and every model. So these are the 3 models. Let's try to understand GLOW first, a very popular model, initial rather we should say 2014 model it is, when in the form for the context representation of the words. So it is unsupervised learning algorithm for obtaining vector representation for the words. Then there was evolution, which was BERT. Till date, there are many more variants of BERT which are available, or you can just freeze a few layers of the BERT and you can train it on your own domain data, and it works wonderfully. It makes wonders actually. So bidirectional encoder representation from the transformers it is. It's a pre-trained deep bidirectional representation from the unlabeled text. Okay. Now, here it tried to understand the meaning of the word by understanding the whole sentence from both the direction. So if I'm writing a sentence, then right from the start of the sentence and from the end of the sentence, it will try to understand the meaning of that particular word. So it talks about the position, it talks about the tokens which are there in the sentences. We will see it. And then the most competitive one next, which is ELMO, so embeddings from the language model. So unlike the globe representation, it represents the embedding for the word using the complete sentence containing that particular word. So there is always a debate for the BERT and ELMO that which one is good. BERT is little expensive model. You need huge memory computationally, as it's we do have a small BERT as well. But then if you have the scarcity of the resources or the constraint of the resources, then ELMO also gives good results. So let's try to understand each of the model first, and then I'll show you the implementation. So the GLOF model, it is unsupervised learning algorithm. It constructs the co-occurrence matrix, okay, which tells how often a particular word pair occurs together. So if we are saying if particular two words are occurring together frequently, then they may be more similar, okay, or then we may say that they may have a similar context as well, right? So each value in the co-occurrence matrix represent a pair of words occurring together. So here, for example, I'll show you how this works. So suppose I have I'm happy to be here. Let's say that example is there. I'm happy to be here, and we are trying to understand happy. Okay, in my vocabulary, let's say happy keyword is at index number, let's say 2000. Okay, and then here at 2000 index there will be 1, and for all indexes it will be 0. Now from that, from this, so this is called as one hot representation of a particular word in the form of a vector from the vocabulary. Now I want to represent this particular vector with respect to the dimension. So I may say that I want to represent it with respect to, let's say, v dimension, right? And so what would glove embedding do here? It will represent that particular happy keyword with respect to v characteristics which are available, v dimensions which are available. And then it's again a deep learning model, so there are weights, and then it will construct the matrix, co-occurrence matrix, and then that co-occurrence matrix will get multiplied with the weights, and then at last you will get the vector representation of that particular word. So the vector representation of I. So in other words, you can say that it will create the embedding for a particular word, which will be a real value representation of the word along with its context. So I'll show you when we will implement this model as well. What is the drawback of this model? That it does not solve the problem for polysemy. That means if same word is having different meanings, multiple meanings, then there as the globe embedding works on one-to-one relationship, because it is talking about co-occurrence, so it works on one-to-one relationship. So it does not work well for polysemy, the words which are having multiple meanings. Then the next evolution is BERT. So this is a bidirectional encoder representation from the transformers. So it makes use of transformer, an attention mechanism that learns contextual relations between the words. It's an encoder. It has got only encoder, decoder. It doesn't use decoder when it is training or understanding the model, or training the model by understanding the context. So when I'm saying attention mechanism, so what is the meaning of this attention mechanism? Suppose let's say, for example, what is attention? I'll try to show it, tell you at little superficial level. If there are 10 layers, for example, and some learning has happened in the first layer, second layer, third layer, and so on and so forth, till the 10th layer, your model may forget what it has learned in the first, right? So there, the attention model will try to aggregate what it has learned by, let's say, for example, very, very basic operation, let's say, for example, sum. It will just take the sum of the weights and it will carry that till the 10th layer, and there it will aggregate this by adding this attention layer. You can say that you have aggregated the knowledge of all the last 10 layers, and this is how it will try to make sure that it will try to make sure that the relationship between the long distance words will also get captured. There is one more very important and beautiful concept in BERT, which is called as masking. So basically, BERT was invented for sequence prediction task. So in the sequence prediction, that means the downstream task could have been like, for example, predicting what could be the next word. So while training only, it was making sure that my model will generalize well in the future. So it was masking 50% of the words in the sequence. And then the model was trying to predict whether it can predict it well. And if it can, and then accordingly, it was learning from the losses and adjusting the weights. So this masking is there in the BERT, because of which it also deals with out of vocabulary words. And it tried to understand whether my model will work well, even if it is dealing with the words which it has not seen. There are a few downstream tasks for which we also add the classification layer on top of the encoder output, and then multiply the output vector by embedding matrix. So this is how you can see it here. The transformer model from the 2014 paper. I'm showing you that model. So this is how it will calculate the probability of each word in the vocabulary and predict it. Predict it as in, or for example, you can say when we are talking about the embeddings, it will try to find out the real value representation of each and every token. The next, but as I've told you, what can be the drawback of it? That it is expensive. It needs quite a lot of memory because it is being trained really on a huge data. The next model, Elmo model, it is a deep contextualized word representation that models both one, complex characteristics of the words, and how these uses vary across the linguistic context. Like so in other words, we can say that it is trying to understand the morphological cues from your words. So if from the character, so when I'm talking about the whole word, it is also learning from the each and every character of the word. So when it is learning from each and every character of the word, then you can say that even if in future it is dealing with the words which it has not seen, but the understanding is at the character level, it will understand, it will capture the cues, morphological cues from the word, and try to understand that word on which it is not being trained, right? So these word vectors are learned functions of the internal states of the deep bidirectional language models, which is pre-trained on the large text corpus. So you can see it here. It's a bidirectional. So these are long and short-term memory models. It learns in both the direction, forward and backward. But here the drawback is that it concatenates. So as it concatenates forward and backward model, sometimes it does not actually take advantage of this bidirectional learning. So because of this concatenation, as someone mentioned in the chat, it may lose some of the information which it has learned exhaustively. So yeah, but then it works well with the computational constraint, with the memory constraints. So my choice when it comes to using the word embedding models, my choice is that I usually try to see that how much resources I have in my hand and how much semantically complex my representation of the data is, and then accordingly my choice is between the BERT or ELMO. For my PhD research work, wherein I'm working in the healthcare domain, I have used BioBERT. I have used clinical BERT as well, using which I tried to extract the clinical named entities from the electronic health records, and then we performed some. We extended this work for identifying some more information from the patient record. But then if you are not performing any domain-specific tasks, then BERT and ELMO gives you best output. When it comes to constraints about the resources, then ELMO also gives you good output. So now I'll try to show you the implementation. I'll try to show you the implementation of the model which we have used, we've been using in our college. I did not, as I've told you earlier, that I'm just using the pre-trained model here and trying to achieve the goal. So the first, I will just compare this. Let's start with the globe in the same order as that of, I hope the screen is visible. Is the screen visible? The Colab notebook is visible? Yeah, okay, great. Thank you. Yeah, so let's try to understand Glove here. The first thing is I've downloaded Glove from their official website. It takes a good amount of time. So I have executed this notebook earlier only, and then I'll be showing you the results. I'll be showing you the results here. So I've downloaded this Glove model, and now from this Glove model, yes, you can see it here. Now stored it, set the path, and this is what the list of project titles which we have. So I'm considering these are the list of projects which are being already done by my students for last 2 years. And now whenever a student is submitting a project title, I wish to check that project title. The model which we have, is there is some question in the chat. Let me see what is that question. Caller file. No, I did not understand caller file. The collab. I'll share. I'll share this notebook as and when we've done. I'll share the notebook here at the end of our presentation so that you can use this. Okay. Yeah. Okay. Okay. So now we are talking about. Laptop's battery is low. Let me quickly connect it. I'm so sorry. Let me connect it to the charger. Just give me a second. I'm so sorry. This is fine. Okay, so these are the list of project titles which were submitted by my students for last 2 years, and our aim was to make sure that the next project title which would be submitted should not be in the similar context as well. It is not only that the title gets repeated. We do not want students to repeat the same, the similar kind of task. So we thought of using this embeddings to perform this task. So here, these are the sentences, or these are the list of projects. This is the query. Here you can see that model.build vocab. So it is building the vocabulary from these list of project titles. So my vocabulary, I told you that we need vocab and we need dimension here. I'm using the default dimension, but the vocabulary will be built from the project titles which are being submitted. Now this is the project title, let's say for which student is submitting. Auto build generator is the project title, and now I want to find out whether there was a similar project which was being done in last 2 years. So I'm encoding this particular query which is submitted by the student, or we can say that I'm converting this auto build generated into a vector by using the Glove embedding. And then this has converted, this has already given me the vector representation of so vector represent so here I'm converting the query which is being submitted by the student into the vector by using the Glove vector embedding. Now I need to find out the similarity between this vector along with the vector representation of each and every title which was implemented in the last 2 years. So here what we are doing here, we are simply using the cosine similarity to do this and trying to find out the similarity as 1 minus distance between the two vectors. So here, this is query vector is the variable in which I'm storing the vector representation of the query or the title which is being submitted. And then now here I'm running uh, uh, through the sentences and trying to find out the vector representation or trying to generate the vector representation of each and every project title. And here I'm calculating the similarity, okay, the cosine similarity between the project title which is submitted by the student with respect to each and every project title which was already implemented by the students. And then here I did not restrict it to any number. It was just calculating the similarity with each and every project title. And then I sorted it with respect to the highest similarity being printed first. And then you can see that the first title which is there in my list of project is web development, and the similarity of auto bill generator is 0.53 with web development. You can see the vector representation of the web development is this, and the similarity of auto bill generator with web development is 0.53. In the similar way, it is finding the similarity of auto bill generator with machine learning, which is 0.49, and so on and so forth. So criminal face detection using machine learning. These are the project titles which are implemented by the students, and it is showing me that how similar it is. So I can see the topmost similarity for the project auto bill generator is 0.49 or rather 0.53. So the topmost similarity is 0.53, and I can now manually check that, okay, I can say I'll just check first 10 most similar project titles, and I can see here that the similarity is very less, so I can accept this project title. Okay, so this is using the globe embedding, but then it does not work well if the similar kind of, because there was not even a single project which had these keywords, auto, bill, generator. So that's why it couldn't find the semantic similarity. It could not find. There were few projects which were a little similar in context with this, right? But then still it couldn't find the similarity of it. Rather, sometimes the results were really vague. So we tried to use a better model for this. And the second model which we studied was BERT. And we have used sentence BERT here because we wanted to represent each and every sentence as a vector, the project title as a vector. So again, I'm using the transformers which are available, the default. I've downloaded these transformer models here. And now these are the list of the projects. But here, instead of finding the similarity of my project title with each and every project title, I thought you give me only first 10 topmost matching project title. And here I tried to change my query as well. Yeah. So here you can see that using so the whole corpus, the list of project titles, are encoded by using the BERT encoding first. So model.encode will convert each sentence into a 1D vector with the 78 column, means the representation dimension of each and every vector. Here you can change it in the default settings. And now the query. So the topic which I entered was implementation of the word embedding. This was the topic which I had given as an input because I'm taking this dynamic input from the user, as we wanted it to be like the project title is entered and then check the similarity. So here now I'm saying that I want only the top 10 matches. And then it is again calculating the semantic similarity and attaching, of course, it is attaching the query and giving me that how much it is similar with the first top 10 titles. So you can see it here, just simply printing the cosine similarity. So it was giving me little better output as compared to below. So the top 10 most similar sentences in the corpus, text summarization. The query which was submitted was word embedding. So you can very well see that it has captured the context. Text summarization was a project title, and it has given the highest similarity of 0.87. Word prediction system, then document digitization, book recommendation system. You can very well see that the domain of these projects is natural language processing. Research paper recommendation system, sentiment analysis, prerequisite MOOC courses recommendation based on the syllabus, image caption generator, detection of manipulated facial images, and product review sentiment analysis. Now, there were project titles other than this as well that you can see: AI virtual printer, email spam filter, competitive coding platform. There are many more project titles as well, but it has very well captured the semantics, which is nothing but the context, we can say, right? So this is how Glove gave us little better, but it took much more time. It took almost 1 hour, 1.5 hours for me to train only on this small corpus. Hardly there are 40 titles, project titles in it, not more than that. So if I keep on increasing the size of my corpus, definitely the time which will be required to train will be much more. So the next thing, so the constraint, as I'm working in the collab, it may exhaust my memory. So the next model which I try to use is ELMO. So with the language model embeddings. And then again, I'm using the same project titles. You can see I've downloaded. Yeah, for the ELMO, the constraint is that you need a TensorFlow 1.15. If you use, usually when we use Colab, it downloads TensorFlow 2, and then it gives you many issues when you are dealing with the dependency packages. Okay, so now here from here I've downloaded the model, and now I'm creating the embeddings for the project titles again. My pipeline of work has not changed. I'm just changing the model, language model for this. And then now here we can see that it is giving me the embeddings for all the titles, project titles. And here I'm giving the input. So this is the topic. Again, I'm working in the similar fashion that I want the topmost 10 titles to be printed. For the query, again, I'm constructing the embedding or the feature vector, context feature vector for it. And then I'm simply calculating the cosine similarity between the search vector, and X is my list, which is containing the vector representation of each and every title. It is list of list. And then converting it into 1D. So that I can sort it with respect to the cosine similarity. I want highest to be printed first. And then you can see here that it gave me, yeah, you can print the cosine similarity, which I forgot to print. I commented it, so it couldn't get printed. But you can even print the cosine similarity. So it is with respect to the cosine similarity, now it is printing. Word prediction system, distributed finances, text summarization, document digitization, Medbot, 2D simulation of the complex data structure, DigiSat-12. It means this is a project which talks about in India we have a system, a government system, wherein whenever you buy a land, you need to submit a document to the government which is called as Sat-12, and digitization of that particular process is called as DigiSat-12. Image caption generator, AI virtual printer, and sentiment analysis. So these are the project titles which are given by the ELMO. So when I try to compare that, how, like when I try to compare my BERT embedding especially with the ELMO embedding, why like the choice is difficult here, we can say, because it is totally domain specific. You can say that I'll be using BERT because I'm having resources, because BERT is really trained on a huge data and it really gives wonderful results as well. But then for the ELMO as well, as it captures the contextual representation of each and every word, it also captures the representation of the word by the deep combining all the layers by deep training it. And as it is a character based model, so it deals better with the out of vocabulary word as compared to BERT model. So going back to our presentation, what we found, the BERT was giving us better output, but when we tried to give all the project titles, it was taking much more time for us to give the output. So we were really happy with the Elmo results. So now let's get back to the presentation where we were. So the most important thing is we can use the models which are available, of course, but then what are the open research domains in the word embeddings? So nowadays, it is when we are talking about understanding the languages, initially when we started understanding the languages, we were talking about understanding the language with respect to the dictionary. So to understand English, we used to maintain the English language dictionary, and we were trying to understand that particular word with respect to the dictionary. We have many more downstream tasks which are very much dependent on the dictionary. Like for example, we have lemmatization, we have stemming. But then when we are going little further in understanding our text more and more, then there is a concept which is a new concept which is called as sense embedding. So we are not only representing the word, we are actually representing the meaning of that particular word, so that it will deal with the polysemy. We have seen that all the models, all three models which we studied, were not well versed with the polysemy if a particular word is having similar meaning, right? So the open research domains for the word embeddings are still there, that we can have sense embedding models which can be generated. We can have multi-sense embeddings as well, that one word can have many senses as well, right? There is something more than this, like when it comes to dealing with the context specific task. So we are always having scarcity of the embedding representation for the particular domain. Like for example, legal domain. For the legal domain, legal BERT has come recently, but then still we want the embeddings to be more precise by training the model on the data which is annotated in that particular domain. And this is also very interesting research domain which is available, which is temporal embedding. So temporal means it is with respect to the time. So here you can see I've taken again this diagram from internet. So here when we are talking about Obama, then when I'm talking with respect to the time, then 2009 to 16, the characteristic with respect to which this particular keyword is represented are different. Now when I'm talking about this particular keyword for 2007, then the characteristics are different. When I'm talking about 1990 or 2006, then the characteristics with respect to which this keyword is being represented are different, and these are called as temporal embeddings. In the healthcare domain, it has got tremendous application. Like for example, the domain in which I'm working is non-communicable disease awareness. The non-communicable disease awareness is why we need early identification of non-communicable diseases, because these are the diseases, if they are detected in early stage, are prevented. So the morbidities like heart diseases, lung diseases, or cancers can be prevented if they are detected in early stage. How can I detect a particular disease in early stage? If I understand the symptoms of that particular patient with respect to time. So if I observe the history of that patient for a particular time period, and if I can understand the transition of the symptoms from one time domain to the another time domain, and if I can have the embedding representation, temporal embedding representation of the symptoms, then I will be able to understand the information related to the time for the symptoms towards that particular disease. And then we never know that we will be able to identify, or we'll be able to detect that particular disease in very much early stage, and that would be a great application for the humankind. So there are again many more models which I did not discuss, like What2Wake, Doc2Wake is there, XLNet, XLM, Robota, BARD, Electra. These are the models which are also equally popular, but uh, the output of these models is more or less similar when you compare it with these three major models. So I thought of taking these three models, and it will very well open your doors for rest all models which are available in NLP. Yeah. So this is all from my side. Thank you so much.
Thank you, Dr. Mahajan. So there are chat stuff. I guess they're all done. Let's see anything else.
Thank you. Thank you.
Okay. Thank you for the time. I appreciate it, and I appreciate everyone, audience, for their participations. It was good, engaging program.
Thank you so much. Thank you for
So I hope to see you in another one. Bye.